Thank you all for joining our Applied PDE seminar this Thursday. It is a great pleasure to introduce Professor Vera Hur from University of Illinois at Urbana-Champaign. Professor Hur got her PhD in 2006 from Brown University, after which she became a Moore instructor at MIT. And I believe she's been at Illinois since then. She is currently the Philip Tondeur Scholar in Mathematics and the Brad and Karen Smith Professional Scholar of the College of Liberal Arts and Sciences. She's distinguished applied mathematician, has gotten quite a number of acknowledgement, an NSF Career Grant, a Sloan Fellowship, and many others. But for the purpose of keeping this introduction short, I will hand it off to her, and I look forward to a very interesting talk.
Thanks, Bernard, and the other organizers for the invitation. That was a quite introduction. This is a joint work with Zhao Yang, who is a postdoc here at Illinois, and it is based on our very recent work. In fact, the archive preprint was just posted this morning. Okay. Stokes, in his 1847 paper, he laid out the mathematical foundations for periodic traveling waves at the free surface of a two-dimensional and infinitely deep, this is just for simplicity, and a rotational flow of water. The motion is acted on by gravity, and throughout this talk, I will neglect the effects of surface tension. Among many things he did, Stokes wrote down first terms in the seed power series expansion of the solution. When the amplitude is small, the technique now known as the Stokes expansion. He even sketched what the solution must look like, and here is his original sketch. The existence matter of Stokes waves was treated rigorously in the 20s by Nekrasov and independently Levchivita in the infinite depths and by Sturek in the finite depths, but all for small amplitude. Large amplitude theory began in the early 60s by Krasovsky and many others. And now this subject is in full swing. And I have no time for its very long and rich history. So I'm going to conclude this slide by quoting this famous paper by Benjamin-Feir in 1967. They say that saying, therefore, there has been no doubt that the Stokes waves are theoretically possible as states of perfect dynamic equilibrium. But Benjamin, in the mid-60s, he had the difficulties creating these waves in a laboratory setting, and here his experiment. He had a long wave tank with a wave maker on one end, which will produce periodic wave trains running downstreams, as you see on the left. And after such a wave train traveled a long distance, there for a long time, and during that time, there were some disturbances. Benjamin found what you see on the right, and he thought that Stokes waves, while they exist as the solution to a mathematical equation, they might be unstable. Shortly afterwards, Benjamin offered a theoretical explanation of his experimental finding, and with them, about the same time, but completely independently, reached the same conclusion that a Stokes wave of small amplitude, and by the way, this talk is exclusively about small amplitude. So a Stokes wave of even small amplitude is unstable in sufficiently deep water. And what that means is the wave number of the unperturbed Stokes wave times the fluid depth. This dimensionless quantity that measures the shallowness of the water or equivalently the shortness of the wave. If this quantity is greater than a critical value, which is approximately 1.36. This phenomenon goes by the name of the Benjamin-Feir instability in the water wave context, but more generally, modulation instability, because this phenomenon occurs in many physical situations. Similar results arrived about the same time, but completely independently because this was during the Cold War, by researchers from all over the world, like Till, Zakharov, Ostrovsky, Benny, Newell, many others. Later, Zakharov and Ostrovsky wrote an article about the early history of modulation instability, and to quote, the idea was emerging when the time was indeed ripe. Fast forward 3 decades, Bridges and Merca, in their 1995 paper, they proved the spectral instability for a Stokes wave when it is subject to this instability condition in this box. And I have to say that the original arguments of Benjamin-Feir and all these people, while they correctly predict the physical phenomenon, it seems very difficult, if it is not impossible, to take these arguments as they are and put them in a functional analytic setting for a proof. And the spectral analysis of Bridges and Merca here, it is a way to justify rigorously these former arguments in the 60s. But there are some important open problems. Number one, the proof of Bridges and Merca breaks down in the infinite depths, although there is a former argument by Benjamin-Feir that predicts that all Stokes waves in the infinite depths, they are unstable. The reason for this proof of Bridges and Merca breaks down in the infinite depth, roughly speaking, is because some operator in their proof becomes non-compact, so that they were unable to apply their standard manifold reduction technique. Very recently, in fact, the archive preprint was posted in July. Newell and Strauss, they found a way to overcome this non-compactness issue, and they finally proved the Benjamin-Feir instability in the infinite depths. And last month, I deposited an archive preprint for a different proof for the same theorem. So this item number one is no longer open, although there are still many more things to do. Number two, modulation instability, generally speaking, is about, so you have a perfectly periodic traveling wave, you modulate, and how these modulated waves will vary over a very long space and time scale. Translating that into spectral analysis language, it is all about what's happening near the origin of the complex spectral plane. The proof of Bridges and Merca is focused, targeted at the origin of the complex plane, and it provides no information about what's happening out a bit away from the origin. And this talk is about this item number two. And last but not least, can we promote spectral instability to nonlinear instability? Or is there some nonlinear stabilizing effect? This item number three is, of course, very, very hard, but there is some progress, recent progress in this direction by Jiulin and his collaborators, although this work is still at the level of simplified model equations, not for the waterway problem. Again, this talk is about item number two. McLean, in his 82 paper, he numerically studied the spectral stability and instability of a Stokes wave in the finite depths, where the depth is bigger than or less than 1.26, this critical value. And he had earlier papers for the infinite depths. He reported that spectral instability away from the origin. And I'm going to say few things about spectrum for this problem. So here is the real and the imaginary axis in the complex plane. And the spectrum is symmetric about the real and imaginary axis. So that the spectral stability means that the spectrum is completely contained in the imaginary axis, and any unstable spectrum must be accompanied by its symmetric reflections. Now, the waterway problem is a Hamiltonian system, and it is in general true for an Hamiltonian system with the full symmetries. that a necessary condition for spectral instability is that two eigenvalues collide at the imaginary axis with the opposite Crane signature, which I'm not going to define in this talk. For the water wave problem, when the amplitude, which I'm using epsilon for, when amplitude is 0, then the trivial solution with a 0 surface and 0 fluid motion, such a trivial solution is, as we expect, stable, and the spectrum consists of the imaginary axis. Now, a little calculation will tell you that there are countably many points along this imaginary axis where two eigenvalues collide, and this is due to a resonance of the unperturbed solution, unperturbed wave with its infinitesimal perturbations. Technically, more technically, what that means is there are two flow k exponents called that k and k prime, and the flow k exponent, roughly speaking, measures the quasi-periodicity of the perturbations. And here I allow very general kinds of perturbations. Now, so there are two flow k exponents, and the difference is an integer multiple of kappa, which is the wave number of the unperturbed wave. The numerical studies of MacLean and many others later, they all predict that each of this resonant eigenvalue will lead to spectral instability for some non-zero amplitude. Now, Bernard and Katie, in their 2009 paper, they focused their study near those resonances, and they present a full spectrum near those resonances, which was not present in earlier works. So on this slide and the next, these plots, they are happening in the complex spectral plane, and these curves, they represent the spectrum for the Stokes wave problem. In their setup, the wave number of the unperturbed Stokes wave is set to be 1, so that this depth, it measures the shallowness of the water, or equivalently the shortness of wave that appears, that is a dimensionless quantity that appeared in the work of Benjamin and Witham. Now, first, when the depth is 1.5, this value is greater than the critical value 1.36 something, so that the underlying Stokes wave behind this spectrum is susceptible to the Benjamin-Feir instability, which manifests as this unstable spectrum that comes off the imaginary axis at the origin. And if you zoom in, then you see what's on the upper right corner. This is not new to us. In fact, this is exactly what Bridges and Muka prove. But the numerics shows additional unstable spectrum that comes off away from the origin of the imaginary axis, and this location is precisely the resonance of the lowest order, order 2, and if you zoom in, you see a bubble of instability. You may find more unstable spectrum as you run off from the origin along the imaginary axis, but it seems that in this situation, modulation instability near the origin is a dominant one, with the largest real part of the unstable spectrum, which will correspond to the fastest growing mode for the linearized problem. So that such a additional unstable spectrum, while it may provide additional spectral information, it may not probably alter the wave dynamics to the leading order. But now when you take this steps to be 0.5, this value is less than the critical value 1.36, so that the underlying Stokes wave is no longer susceptible to the Benjamin-Feir instability. And in fact, there is no unstable spectrum coming up from the origin of the imaginary axis. But the numerics nonetheless shows unstable spectrum. They all comes off from resonant eigenvalues, and each and every one, if you zoom in, you see a bubble of instability as you see on the right. So that in this situation, the underlying Stokes wave is not the Benjamin-Feir unstable. but it is spectrally unstable nonetheless. And in fact, all these numerical studies, they teach us that there are more unstable Stokes waves than what the Benjamin-Feir instability finds. This has been completely open problem analytically. Not only there has been no rigorous proof of this fact, but also there has been no formal analysis what's analogous to what Benjamin and Widham and others did for modulation instability. And I'm going to present what I think it is the first proof of such high frequency instability. Now, it was Bernard who suggested this name, the high frequency instability. And in fact, it was Bernard who suggested this interesting problem to me. So special thanks to him. Now, the idea behind this name, the high frequency instability is, so when this instability occurs, then an unstable solution to the linearized problem will take the following form. It's e to the lambda t times some function of a spatial variable. And here lambda is the spectral unstable spectrum, so that it has non-zero real part. And in this situation, the instability happens away from the origin, so that the imaginary part is not so small, so that such a solution will be exponentially growing while rotating in time. And this behavior is quite different from modulation instability, for which lambda is near the origin. Now, let me discuss some of the main ideas of the proof, more specifically, what we're doing different from the people before us. So suppose that we formulate our spectral stability problem using abstractly an operator Kelly-L, and this operator depends on at least two independent parameters. Epsilon is for the amplitude and K is for the flow K. And what the Bridges and Milka did, first, we drop the flow K exponent. Then the situation is you are dealing with the co-periodic perturbation or the same periodic perturbation as the underlying unperturbed wave. Then we want to completely analyze the spectrum of this operator at the origin. And this is possible because the water wave problem is Hamiltonian. It turns out that there are 4 eigenvalues at the origin of this operator with a Jordan chain of length 2. We also have to compute its eigenfunctions explicitly, and this for small amplitude, and this is possible using the Stokes expansion. With this full information of the spectrum at the origin for zero flow K exponent, we now turn on flow K and we see how these 4 eigenvalues will move around in the complex plane. This idea was not helpful for our purpose, unfortunately, because this kind of explicit spectral information for non-zero amplitude, this is available only at this special location of the origin of the spectral plane, and it gets lost once we depart from the origin. But we are interested in spectrum away from the origin. So we do the opposite in our strategy. So step 1, we turn off, we drop the amplitude parameter. And the situation now is we deal with a linearized problem about the trivial solution. And this operator about the trivial solution, it has only constant coefficients, no variable coefficient, and we can compute this full spectrum, not just near the origin, but the entire spectral plane. We compute the full spectrum explicitly. It turns out that there are 2 spectral curves that wrap around the imaginary axis. And then we turn on the amplitude parameter, and then these spectral curves, they will start to deform, and we see how they deform. And we have to determine that explicitly, again, for small amplitude, asymptotically using the Stokes expansion. And this was the idea that I used for a simplified proof of the Benjamin-Feir instability in the infinite depths. Another aspect I want to discuss, the waterway problem as a free boundary problem. So that the step 0, before you do any of these things, you have to fix that free boundary. In an irrotational flow, which we are in, it is almost traditional to reformulate the 2D waterway problem into a 1D problem by introducing some non-local operator that will relate the information, what's going on beneath the fluid surface in terms of the quantities that are only defined at the free surface. Examples are the Dirichlet to Neumann operator or the AFM method that is familiar to the community in Europe. And that was the reason, one of the reasons why I was working to develop spectral analysis for non-local operators. But that's in my past life. Now, I deliberately reformulate the 2D waterway problem into 2D PDE problem so that I won't see any fancy non-local operators in my reformulation. The reason is that you can develop spectral analysis for non-local operators, but the counts are often not detailed enough to see everything that we want to see. On the other hand, there is a hugely successful work of stability theory for PDE problems, no non-local operators. The waterway problem is a very complicated PDE problem, and I think that this non-local operator, it introduces the extra layer of complications to this problem. So now I want to get rid of that, and I want to put the waterway problem into this stability theory for the PDE problem work. And I want to use the strongest tools in that world to tackle this problem. Specifically, my end goal is to define what people call the periodic Evans function. This is a determinant of an n by n matrix. For the Stokes wave problem, it is a 4x4 matrix for the Benjamin-Feir instability and a 2x2 matrix for the high frequency instability. But of course, this n by n matrix contains all the spectral information of this big problem. And this Evans function is an analytic function with respect to epsilon and k, and also lambda, the spectrum of the problem. And when this determinant becomes 0, then the corresponding lambda is the spectrum for the Stokes wave problem. And I want to say that this periodic Evans function technique, it has been implemented for a wide variety of PD problems, but most of the time it is done in 1D problem. And when I reformulate the 2D waterway problem into a PD problem, I still deal with a 2D problem. And to construct a periodic Evans function for such a cylindrical domain, it is not a trivial matter. So I think that one thing that is useful about what we do here outside the waterway problem is this new way of constructing the periodic Evans function in an in a cylindrical domain, which you can compute explicitly. Now, I want to make sure that I hit the punchline. So let me first discuss the main research that we obtained, and then I will come back to discuss other technical aspects of the proof. So after we construct the periodic Evans function, as a test drive, we revisited the Benjamin-Feir instability, and we reproduced the result of Bridges and Mocha in the 1995 paper. So a small amplitude, sufficient small amplitude, and 2 pi over kappa periodic Stokes wave is unstable if this index function becomes strictly positive. This index function is a function of kappa, which is the wave number of the unperturbed Stokes wave, and it involves hyperbolic functions. so that you can numerically evaluate. And it turns out that it has only 1 0 at around 1.36. So not only we get the same critical value as everyone else, this index function that we get, this function is exactly the same as the index function of Bridges and Milka. And also this expression appears in the work of Benjamin and Witham and others in the 60s. So again, Benjamin and Witham were right. But there is a bonus. So in the course of the proof, we determine explicitly and asymptotically the spectrum near the origin. And these figures, they are plots of the spectrum. They are not cartoon. We evaluate the coefficients of the formula for our spectrum for some kappa, which gives us the Benjamin-Feir instability. And as we vary kappa, and these the qualitative behavior of these spectral curves, that they remain unchanged. So this is genetically what's happening when you have the Benjamin-Feir instability. Now, there are two distinct spectral curves. They come up from the origin in the first quadrangle, and the rest of the quadrangles are by symmetry. So there are two spectral curves, and we have two spectral curves because when the amplitude is 0, so everything gets squashed into the imaginary axis, then there are two spectral curves which have the opposite curvature at the origin. So when we have add absolute effect, then when they come out of the imaginary axis, then they have a different curvature. And we think that each of this curve will make a closed loop. So the solid one will make a figure 8, and this dashed one will make a figure infinity. Now, if you remember what Bernard and Katie report, so numerically people find that it's a figure 8, but not figure infinity. And we think that this is because this figure infinity curve is a much smaller, it's order of magnitude smaller than the figure 8 one. So it seems very, very difficult to numerically resolve this. When Benjamin-Feir instability happens at this critical wave number, and when it happens, the spectrum consists of two closed loops, one figure 8 and one much tinier figure infinity. But if you only care about which wave is stable or unstable, then we provide no further information, no new information here. Then our new result is away from the origin. And here, so the Stokes wave is going to be spectrally unstable near the resonant eigenvalue of the lowest order 2, if the wave number of this unperturbed Stokes wave is in this interval, whose lower bound is approximately 0.864, and the upper bound is slightly greater than 1. And our analysis detects no instability, so things are stable at the resonance of higher orders up to the lowest order. So that we explain some of these numerical findings, but not all of them. So to compare our result with what Katie and Bernard says, so we have an explanation of this spectral instability away from the origin. But if you look at the number that Bernard and Katie use, their H is same as our kappa. And this 0.5 is outside of the interval of unstable wave number that our proof provides. Moreover, we do not see any instability at the higher order resonances where numerical people report. I think that both the proof and the numerical computations are correct. There's nothing wrong with what we're doing, but the disagreement happens because, well, the question is, how small is small? Our proof is asymptotic analysis, It's about what happens as the amplitude approaches 0. So this is a instability for arbitrarily small amplitude. On the other hand, for numerical computations, you choose some small value for your amplitude. For example, Bernard and Katie, I think they use 0.01 for their amplitude, and that is order of magnitude smaller than what McLean and earlier people used. But still, it is not clear how small that number is. And I think that this interval of unstable wave number, it will grow as we increase the amplitude because the underlying wave becomes more and more nonlinear. So that if we have analysis for small but finite amplitude, then we can hopefully cover the numerical results. But at this moment, we don't have an analysis for finite but the small amplitude. Now, for the remaining time, I'm going to very briefly discuss the proof. And this proof is, by the way, extremely technical. So I'm going to only hit the high points. Okay, so step 1. We want to reformulate the free boundary problem for the water wave problem into a fixed domain. And again, here, we don't want to squash the two-dimensional domain into 1D. So what we do is, so when in the unperturbed wave situation, say we have a fluid of depth 1, and then when the fluid surface oscillates around this level 1, we forcefully flatten the surface to this level 1. And that's what this flattening coordinate does. This is not the most elegant way to fix the free boundary for the water wave problem. In fact, this might be one of the worst things you can do to the water wave problem. But it does serve our purpose. But since we are not very sophisticated when we reformulate the problem, as a consequence, we have to deal with the hugely complicated expressions later, and we deal with them by brute force. Another thing that I want to say, we want to formulate our spectral stability problem as a first order ODEs in respect to the x variable, that's the direction of wave propagation. So that we want to break the second order Laplace equation, that is the equation in the domain, in the fluid domain, into a system of first order equations. And that for that purpose, I'm introducing U, which is partial phi and partial x, and here phi is the velocity potential. So after the reformulation, we have a formulation in this box, and the first two equations are rewriting the Laplace equation, and now in the fixed domain, the fixed infinite strip between 0 and 1 in the y direction. And the third and fourth equations are two boundary conditions at the free surface. Now it is the boundary is fixed at y equals 1. And the last equation is the boundary condition at the fixed bottom, y equals 1, 0. And after we find a Stokes wave and Stokes expansion to this formulation, then we linearize this problem about that Stokes wave of small amplitude. And here is the result. So this is already too big to present in a slide, but everything comes with epsilon belongs to the Stokes wave, the stationary solution. Here we have three unknowns, phi and u. They define the velocity of the problem, and they live in the strip y between 0 and 1. And eta is our surface variable. So we need three equations to describe these three unknowns. So we take two equations that are defined in the strip together with one of the boundary conditions to make the equations for our unknowns. And then we're left with the other boundary condition at the top surface and the boundary condition at the bottom boundary. Now, so the two boundary conditions at the free surface for the waterway problem originally, they are both non-linear, so that no matter which one we take as part of the equation and which one we take as our boundary condition, we ended up with an inhomogeneous boundary condition at the top surface. So we introduced an auxiliary variable zeta to forcefully make this boundary condition to be homogeneous so that we can do some function analysis. And this zeta will introduce even more complications when we do calculations. And again, we just power through it. So at the end, we have three unknowns, phi, u, and zeta. And these first three equations, I'm going to abstractly write as an operator equation. You see here in the box in blue. And these two boundary conditions, I'm going to put them in the function space that I'm going to solve this operator equations that I'm not specifying in this slide. And in this equation, I identify the principal part, that's L operator. And this depends on the spectrum lambda, but it does not depend on the epsilon, and it's a constant coefficient. There are no variable coefficient, no epsilon. So all the complications I dump onto this B operator. And now I'm going to first focus on when epsilon is 0. And when epsilon is 0, I'm simply solving the operator equation for this L of lambda, which I can solve explicitly, and the result is the following. It turns out that the spectrum consists of the imaginary axis, and here I'm going to use sigma for the imaginary part of the spectrum, and the sigma is, and also lambda, is parameterized by the Floquet exponent using the well-known dispersion relation of the waterway problem. And the dispersion relation of the waterway problem solves a quadratic equation. So it comes with two branches, plus and minus branches. And here, these figures are the plots of the dispersion relation in the K versus sigma axis. And so these plus and minus branches, they are symmetric to each other, and each branch has the unique critical value. And if my eigenvalue is between these two strips bounded by two critical values, then this sigma will intersect the dispersion relation at 4 points, so that it will produce an eigenspace of dimension 4. But if the eigenvalue is away from this strip bounded by these two critical values, then the sigma will intersect the dispersion relation at 2 positions, so that it will make a eigenspace of dimension 2. Now, I'm going to turn on epsilon, and as I increase epsilon, these spectral curves, they will start to deform, but they deform at least continuously with respect to epsilon, so that when the epsilon, the amplitude is small, then the spectrum is near the imaginary axis. And now, for such a spectrum, lambda, I'm going to split that spectrum into the purely imaginary part that is associated with the epsilon equals 0 plus small perturbation, which has the small modulus. And I'm going to split my operator equation in the same way. And then this principal part restricted at the 0 amplitude. From the previous step, I know that this has a finite dimensional eigenspace, so that I can use the center manifold reduction technique to reduce this ODE, which is set in an infinite dimensional function space, to a finite dimensional eigenspace. And moreover, this finite dimensional eigenspace has a basis that is made up of eigenfunctions, so that I can write the solution with respect to that basis, and collecting all these coefficients, I have n by n matrix, which will solve a first order matrix ODE. And it is a standard exercise to define the periodic Evans function as a determinant of the Floquet multiplier that is pure complex exponential of the Floquet exponent k and evaluated at after one period t minus this fundamental solution to that matrix ODE, which I'm not writing down here, but evaluated at t, and this matrix evaluated at t is often called the monodromy matrix. And roughly speaking, the monodromy matrix measures. So I start at the identity matrix, and after I solve this ODE, and after one period where I am. And the spectrum of the Stokes wave problem consists of the lambda for which this determinant becomes 0 for some Floquet parameter k. And now my effort goes to compute explicitly this monodromy matrix A, and for sigma near 0, so that means the Benjamin-Feir instability. So I deal with 4x4 matrices because my eigenfunction, eigenspace is 4-dimensional. And now, so my center point of the spectrum is 0. And I'm going to make a power series expansion of this monodromy matrix with respect to the spectral parameter delta and the small amplitude parameter epsilon. And the result, the part of the result I'm showing here, you need at least one more term in the expansion to get to the conclusion. Some of these entries, matrix entries, you can determine either by symmetry or by some elementary properties of the problem or from the previous step. But most of the entries, which are long, which comes with long expressions, and they are not so trivial, they are solving to some extent this ODE. And this involves, so that this proof involves solving lots and lots of ODEs and PDEs. But I also want to comment that, so it is clear that there is this projection operator that projects down to this finite-dimensional eigenspace. But that's not enough for our proof. We have to write down the explicit formulas for this pi, the projection operator. And that was one of the most technically difficult part of the proof. Anyways, so you do a huge volume of calculations to figure out all these matrix entries, and then plug in this to the definition of the period Evans function delta, and this is analytic function with respect to all these arguments. So you make a power series expansion, and these are the orders that we need for our conclusions. And now we need to solve this delta function being 0, and we're interested in what lambda will make this root, right? So we want to write our spectrum as a function of Floquet and the amplitude parameter, and we'll have to determine in what fashion this lambda depends on the Floquet and the amplitude, and this is another technical part of the proof. But these are some of the lowest terms that should appear in that expansion. And then we plug in this back to this delta expression, and we solve this equation term by term until we get a sufficient condition for instability. For the high frequency instability, we repeat the same procedure, but now centered not centered at 0, but the centers at the different location. It can be at the resonant eigenvalue or away from it. In fact, we studied the spectrum all along the imaginary axis, not just at these resonant eigenvalues. Now, for away from the origin, the matrix is a 2x2, so in some sense it's easier. But then now this it's not centered at the origin, so all these coefficients becomes much bigger than before. In fact, so just to give you an idea how complicated things can be. So this is a page from our preprint, and the letters are small for purpose. Don't read them. It's not what I want you to do. But so you need 2.5 pages of these expressions, which are already written in a shorthand notation. And to sum it up, all these, it makes the coefficient of one of these forcing terms of our ODEs or PDEs. And this is happening at the order of the lambda to the 1 and the epsilon to the 1. So it's pretty low order, one of the lowest orders. And that's one of these forcing terms. And there are 12 of them at that order. So this is clearly not a human job, and we use the symbolic, we use MATLAB to deal with these symbolic manipulations. And it takes about 2 kilobytes to save the MATLAB data for these expressions. But then we have to solve ODEs involving these expansions, and when we solve ODEs, those matrix entities, it takes more than 500 kilobytes to save those matrix the MATLAB data, so that it is impossible to print out the index formula either in a preprint or on a slide. And that was the reason why I was not able to give the index formula earlier when I was discussing the main result, the statement of a theorem. We do have an index formula, but we can only evaluate that using MATLAB calculation. So one of the most essential ingredient of the proof is hard work that Zhao did for this project, which I cannot underestimate. And with that, I will stop. Thank you.